All right, thanks again for being here. Basically, one of the purposes of this presentation is to compare the gold standard of triple quad for quantitation against Orbitrap. And also quickly look at for possibility of using Q-Exactive, which can only do MS2 data for looking for knowns and unknowns. Perfluorinated compound in 1995, I liked it better because we just call them PFCs, which covered everything. But except now we're finding out that there are more than 3,000 compounds. So now we have to do furthermore classification, such as perfluorinated, which I like to call it active substances, but the reality is alkyl substances. And then we can divide them to two groups. Sorry, where is the pointer? Okay. If all the carbonated backbone are saturated with fluorinated compounds, we call it perfluorinated. If one of the CF, as Paul Jones showed, some of the studies that he showed, even if it's one, then we call it polyfluorinated. But from all of these classes and compounds, the most studies are PFOS and PFOS, which are the C8 compound for sulfonate and carboxylates. There are some phosphonates groups which are like as wax papers, but in landfill they can later on be transferred to PFOS or PFOS as a biotransformer. As we see, this is like an emerging contaminant. We say it's an emerging contaminant because the studies are just started from 1995 because triple quad ESI provide us the technique to look at this kind of compounds, as before in like GCMS was a little bit more harder. So in scientific world, 1995 is pretty recent. As we see, we are getting a lot of information, and every year more publications are coming out. One of the reasons is better triple quads, and also TOF-MS and QE or Orbitrap are contributing to a lot of more studies and identifying new compounds for these classes. One of the things is in EPA in America, every 5 years, based on Safe Drinking Water Act, they look for 30 compounds that they have not studied in our drinking water, and they come up with an unregulated monitoring rule. In the last UCMR3, they chose 6 specific PFCs compounds to be included for their study to see how if there's a need for federal regulatory for the United States. So after from 2012 and 2015, this is the summary of the data. As we see, there are some hotspots, which are due to U.S. military fire training sources. As Dr. Munez yesterday showed, AFFFs can cause plumes, and since these compounds are so strong, as Paul Jones said, that they are very hard to make. But once it establishes, it has the shortest bond, so it is basically destructible once it's formed. That's why they use it for firefighting, because nothing happens to them. So once it gets introduced to environment, they are very persistent and they will remain. But there's also a lot of spaces non-detect. Basically, after 3 years study, we found that only 2% of the drinking water were affected in the United States. However, we also have to look at the detection limits. We were looking at the PFOS 40 ppt and PFOS 20 ppt. Right now, the regulation is if you add these two together, it should be less than 70 ppt. So as far as the toxicology goes, we are in good shape. But if we go to a lower detection limit, in Europe or Australia to down ppt, I'm sure this map will be much more orange. So the level of detection limit that we're looking for also determines what we will find. For this UCMR3, we use EPA standardized EPA 537. So every laboratory, what Dave did and us did, all the data are matching, so we can determine the concentrations. So we took like an EPA 537 and we did slightly some modification and used the QE exactive instead of the triple quad to see, okay, what is the gain and how is the sensitivity compared to the triple quads. One thing with the QE exactive, since it is a hybrid, we can also generate an MS2 fragments and data, which is very the most similar to a triple quad single reaction mode. In the single reaction mode, you can get one by one transition in a serial monitoring, as in a QE exactive, you get all the fragments at once in one concerted run. So you get all the fingerprints. This is the only advantage. And this will qualify like a QE exactive as far as EPA concerns, it is equal to MRM. So if an EPA method is written for a triple quad, QE can be used for detection for regulatory purposes. The setup is very easy. In one of setup is, okay, we're gonna follow like EPA 537 standard. We're gonna do a PRM, which is the same as MRM, so we have except we just add the molecular weight of the precursor, and then by itself it will fragment. We also added a full scan, so we're doing a targeted and untargeted compound at the same experiment or workflow. For full scan, there's no optimization needed. Targeted plus non-targeted, we can monitor. For targeted, we just need to put a resolution, isolation window, and specific collision energy, which I usually like to use the normalized collision energy, because in ion trap, it has a more smoother, or it is based on average, so you don't miss the optimized collision energy. After that, we run it, and we see good chromatography is happening. I think it's worth mentioning that as the chains are getting longer by a CF2, you're adding 50 mu to it, and also it's becoming less polar. So the longer chain, the more it's going to shift to the right and a C18 column. And sulfonates are less reactive than ionic than carboxylates, so they usually, even though they are same equal chain size, they elute a little bit later because they're less polar. The one on the rectangle, these are the ones that were monitored during the UCMR3. So we have a good peak shape, and this is only 2.5 ppt of a 250 times concentrate. So as we see in a full scan, we have good signal to noise. Here's a demonstration of the MS2 data, and good linearity with a greater than 0.999. There's a linear force to zero. The method requires to force it to zero, so if you have a blind contamination, it will show up. And the advantage of one is on the QE, I noticed the linearity is much better than in a triple quad that we usually use. The other additive is now instead of only having like one fragment, now you have the full scan and you have a library. So once you have a retention time, matching spectra gives you really high confidence that it is the compound that you're looking for. Other interesting is on the MS, the area count is, I will show you later, it's smaller than full scan. However, signal to noise is infinite. I mean, there's almost no grass here underneath, which is an important aspect of doing an MS2. Now, if you look at the full scan, we see the same thing, except now we have getting a little bit grass, but the area count is about 10 times higher than, because there's no transition happening in a PRM. So you're getting much higher area. However, if you go too low and you have a very complex matrix, this mass can be shifted because these small grasses can shift and suddenly you don't have any peak. So it depends on the matrix that you use, you have to be watchful. The other thing is isotopic pattern gives you confidence, and again, you have a great linearity. Now comes back to MDL study. For drinking water, EPA has provided like LCMRL, which is a regressional LOQ calculation. Based on us, this gives you the most real, what is your reporting limit, because usually MDL is just based on precision. Now they just added some blank subtraction, but if you don't have any blank to subtract, you're still gonna have like only precision. So LCMRL, what it does is statistically will give you like 99% if you have a hit. There's also an accuracy of plus minus 50%. So for me, this is the real reporting limit that one can put their hat on for further studies. How it's done is like at least 7 different concentration and at least 4 replicates of blank. And then statistically gives you a number. It calculates. But unfortunately, due to the budget cuts, it still only runs on the 32-bit computers. That's the most challenging. Now we did the study, and these are all, everything has gone to the full extraction, and these are the data. So comparing the PRM to full scan, as we see, the both are, even though full scan has 10 times more area, selectivity and sensitivity of PRM is a little bit better or equal. Of course, that's always, in a tougher matrices, that will become more obvious. But as we see, there's really, we can go down like 0.5 ppt of PFOS, much lower than what we need. For this method, the blank or the background determines how low you can go. These compounds ionize very well on ESI. But in addition, since we did a full scan and PRM together, now we can go back our calibration standard, even though we were not targeting these compounds, they were there, but we were able to do the full study on it. For PFPA, C4, and other compound PFPA, also we got good LCMRL or reporting limit. So this proof of the concept that you can put 2 different full scan and PRM at the same run and get all the results that you intended to. The advantage of this is your reporting limit at MS2 gives you much more confidence because more selective and sensitive. But again, later on, if somebody asks you, did you check for PFBA or other compounds, then you can go back and see if you have it or not. That's the advantage of using multiple workflows. However, now we're coming to a question. I mean, PFOS, this has been a very challenging question since 2009, when we were only using triple quads to quantify. For PFOS has 8 isomers. And there are 2 main transition, or the best fragments for sulfonates are like 80 and 99, but which one do you use to quantitate? But as Riddle did a study from a serum, they found that there's 11 isomers, and compared to the linear isomer, they all have different response factors. So if you use 80 is high bias, 99 is low bias. EPA 537 has decided to use 499 to 80 because there are more isomer branches present. And outside the United States, I have seen many literature that using 99 mostly. But however, once we use like a QE and a full scan, we notice that the best result comes actually using a full scan data, because full scan doesn't matter what the transition or response factor is, it will give you better, accurate, more data. This is an example of the challenging, even if your calibration standard has an isomer, vendor to vendor, the branch isomers, or let me go back. From 11, usually you get all the 11 if you run a one hour run to separate all the isomers. But in practical quantitation, we cannot run a multiple hour run. So all the isomers become combined. It looks like almost like 3 isomers when you're doing a normal run. So in here, the branch isomers, usually on the technical, PFOS is like about 30%, and from this one a little bit less. But if in a real sample to sample could be different. So there's a quantitation dilemma. But if you look at the full scan, use full scan, it doesn't matter how you calibrate it, it will give you more, to me, more practical numbers. So we did the full scan, and it shows this is if the full scan is 100%, full scan over transition 80, 99, and average. They all look like looks like a full scan can give you a better practical data. So when it comes to branch isomer with a different ratio, it looks like a high res with a full scan actually can give you better data than an MS2 data. Then there was during the UCMR2 at the end, there was a notification from EPA that there's another challenge. Everybody knows about sulfonates having isomers and branch isomers, so everybody was integrating. But when it came to carboxylates, some labs wouldn't include the isomers because they didn't know that, they thought that there was artifacts. So we use the Orbitrap to and provide some information for EPA to use. And these are some of the data. Before 1970, PFAS was also used by electrochemical. That's why if there's a firefighting canister from 1970 and if it was used, it could be shown that, okay, the PFAS with the isomers. However, luckily, the main transition of 369 matches with the full scan very good. So there's not a really difference like as in 1980. If you use for PFOS, it could be greater than close to 50% difference, high bias. So in here, for PFOS, there was no much difference between full scan and 369. Now, if you look at the PFOS technical branch, maximum, if you didn't include the isomer next to it, it would come to about 20% low bias. But of course, sample to sample is different, and these are in the real samples. So in general, maximum 24 to 14% difference of being low bias if you don't include it. Luckily, that means that the UCMR 3 results in general were acceptable because only very few lab locations had a greater than 70 or close to 70 PPT. And they repeated the analysis and not much changed in the final results. The additional, with the Alderon, now we could go look at like one of the samples. And since we did a full scan, we were able to do PFDS identification with an isotopic pattern. So this is like looking for, since we have the standard in our calibration standard as an extra target, we are able to identify it from suspect to confirmed. But however, Orbitrap has many ways of using it. The other way would be looking for non-target, unknown or unknowns. Or before I go there, sometimes I get a question, okay, how sensitive is QE compared to triple quad? Of course, it's an apple to orange comparison, but here's some area count from the same standard injected in a Quantiva, which is one of the highest sensitive triple quad available. And with the area count, it's about 5 times less than full scan in area count just only, and about twice as much as in MS2. So this is apple. We cannot say, okay, this is more sensitive or that sensitive, but in general, this shows that the QE is at least as good as compound dependent as Endura, a little bit less than Quantiva when it comes to sensitivity. Now looking for unknown, from here we can drag in different experiments or even combine them. For this purpose, we got a contaminated groundwater from a AFFF site that we had it, and it was like 2 years old at room temperature. But to see, okay, what compounds we can see, even though, because most of them are persistent. So we're doing a full scan, data dependent, MS2, top 5. So it takes the 5 of the highest intensity and automatically fragments it. But usually after gathering all this data, it is very important to have a software like Compound Discoverer to help you to mine the data, because there's a lot of data and you need to have something to filter it so you can really zone in into the data. One of the reasons is because just based on this formula, we have about more than 2,500 data points of different compounds. It was detected and fragmented. However, if we zone in and we know what we are looking for or have some specific criteria, like 1-hydrogen alkyl, RDB 0, isotopic pattern of sulfonates, sulfur compounding, or nitrogen, we can use mass defect. Molecular atom is fluorine is 9, molecular weight is 18.999. So if you have a lot of fluorine, you get a huge mass defect, which is unique to for this class of compounds. So mass defect, negative mass defect works for this type of compound. But unfortunately, fluorine is a single isotope, so you're not going to get much of distinguished infiltration. But by using this, we see these, and then by knowing that as the chain increases, retention time increases, and once you add the CF2 is equal to mass of 50, then we can see a pattern. And once we make this, and then we can dig into more to find more. Here is like PFOS that we identified. Here now we have at 70 resolution, and we ran it at 140,000. This shows that the higher resolution that you go, it adds to the confidence in the MS data, because now you can look at the trace level, like from sulfur trace level isotopes. Now you can also make more distinction. So these are the isotopic pattern. And also the software can show you the fragments for MS2 data. Fortunately for like PFOS, they're using 9 series and 0 series, because either the fragments, they end up in 9 or 0. If there's like a SO3, they usually end up like in 0, and the fluorinated backbone is usually in 9. So we call them 9 series and 0 series. So when it comes to fragmentation, unfortunately the softwares, Mass Frontier or any other software, they don't do it as a good job as any other organic compound, because fluorinated compounds, they have different properties, and it's very difficult to expect what kind of fragment they're going to get. But visual comparison and with some of the rules, one can get more confident. But it has to be done a little bit more manually than usual. Again, like the software, one thing it helps, you can use the MS and MS2, and also custom explanation. So you can draw your own based on a predicted formula, a structure, and then later on it fits to your math. So these tools are not the final answer, but it gives you a lot of, saves a lot of time going over the data. A good tool to have to use. So basically, after doing all that, then we were able to, like for that compound, from groundwater, contaminated compound, we were able to find C2 to C8 of sulfonates. It's important to, so the match and C9, it looked like it was 50, almost 50 MU out, but the MS2 data didn't match, so we had to cross it out. But we found all the other ones. And it's important to say that C2 and C3 sulfonates, there's no commercial standard, as far as I know, available. But they are becoming more important, because if you have a plume, these smaller compounds, C2, C3, they move faster because they're more ionic, so they are ahead. So if you find a contaminant, that means the longer chains might be coming there. So, and another thing about software, if you have like a study and different samples, you can detect where the plume is and where is it spreading, because these compounds don't contaminate in a linear fashion. They go all over the place. They have their own properties. And using all these tools, then we also were identifying some of these compounds. Some of these compounds, from custom explanation, some of these compounds I have seen in literature, so I'm sure it is. But again, there are some more complex compounds that I haven't seen this one or I'm not familiar with it. So these are mostly, I would consider them suspect. They need to be either find a standard to run it to identify it, or you have to take it to second level, do an MSN or MALDI to see, okay, is it really made of these compounds? So in general, we were able to find these. Among these that we found, there are 2 telomers are known to produce the 2H, like PFOS, unsaturated PFOS at the position 2. So these are becoming more important because in wastewater, we are finding a lot more concentration of these, and these are very persistent also, as much as almost like PFOS. So it is good to study, which is an advantage of looking for unknown. If you find other persistent compound that it might be interest in the future. And telomere and sulfonamide, according to world, I think they're contributing almost like 0.5 to 1% of PFOS, or PFHXA, other ones doing the biotransformation. With that, in conclusion, I think we saw that the Q-exactive HRM can work as good as a triple quad in quantitation. And a full scan can work for better, like for compounds with the isotopes that can have a different response factors. It gives you a better, less biased results. Routine quantitation, like running EPA 537 for regulatory purposes and adding another experiment like full scan can be done at will for non-target routine and non-routine. HRM data processing, like a data compound discovery software, can save much time and makes the data filtration much easier. And of course, when it comes to unknown, other techniques can, if there's no standard available, other like MSN and 3C NMR, it is required to really feel that you found the unknowns, which I think Hassan will be showing you later.
Thank you. Okay, any questions for Ali?
The 499 to 80 transition has not been used or commonly used because there's an interference from thyroacetylcholine, which has the same transition. But if you look at the accurate mass, they're different.
Yeah.
Have you been able to resolve them? Have you seen that in your samples?
Well, in our sample, yeah, in the high res, you're not going to see it because it's way off. It's less greater than 50 ppm difference, I think. In a low res, yeah, you can as a false positive.
But when you're scanning, you should be able to see 2 peaks.
2 peaks? I haven't looked for that compound specific.
Okay.
Yeah. But yeah, in a low res, that can cause false positives, definitely.